Did not start the recording. Okay, so now we're recording. So again, this is Conics. This is what I would consider the toughest chapter or section in this unit. It's all application based, so it's all applying what we know about conics, each different type of conic into a real life scenario. So my first one here, because this is a minus, I know that we're going to be working with a hyperbola. Because my y is first, I know the hyperbola is going to be opening up and down. So just from looking at the equation, these are things that I can conclude. So here's what it's saying. The shadow cast by a lampshade has a boundary in the shape of hyperbola defined by the equation, and here it is. What could the center of the hyperbola represent? So visuals are always good. So we have a lamp. So here's my light bulb, you know, me and my artwork here. It's not very good. So my lamp, something, you know, like that. So it's got its lamp shade. And we have our light bulb. So when it's turned on, when our light bulb's turned on, we're gonna have a shadow produced from this lampshade, right? So the shadow is gonna come down like this from the lampshade, right? So it's saying, if this is going to represent a hyperbola, this idea of this shadow going down, what would the center of that hyperbola be? What could the center of the hyperbola be? The location of the light bulb, the bottom of the lampshade, the top of the lampshade, or the vertex of the shadow? So my thing isn't actually probably the best thing to be looking at, because this looks like it's the vertex of the shadow. That's not the case. So where does this shadowing start to happen? It happens because of this light being projected off. And so when it's being projected off, it's aiming down. And that's happening right at the light bulb. The whole reason the shadow's happening is because of our light bulb, right? It's happening because this light bulb is shining this light everywhere. And so that shadow happens right here. So this would actually be the center of that hyperbola. So it is at the light bulb because that's where it's being produced. That's where it's starting. And so there you go. So kind of tricky because obviously this looks like I drew to the bottom of the lampshade, just coincidentally where it happened. But again, that shadowing starts as soon as it hits that light bulb and starts going down, that shadowing of it is going to start happening. So again, kind of visualizing what's going on. Let's see. The orbit of a comet in a video game can be defined by this equation. Which of the following is true about the path of the comet on the screen? Okay, so this right here, since it's a plus, we know we're going to be working with an ellipse. I know that the center of my ellipse is going to be at 56.28. I know that this value is my a squared. So a, if I take the square root of 150, it's going to be 5 square root of 6. Let's see calculator that because it's easier to grasp. So 5 square root of 6 is going to be approximately 12.2. Just so when we graph a quick visual, you guys can see that better. My b squared is 256, so b is going to be equal to 16. All right, again, I'm all about visuals because these are just answering questions about an ellipse. All they are is about an ellipse. So this comet, this orbit of the comet is just going to be an ellipse going around. And then they're asking all these questions. So let's look at that picture of the ellipse. So I know then my center is going to be at, we're going to go here. This will be 56.28. So here's the center of my ellipse. And I know that my A, I'm going to go 12 in each direction, right? I'm going to go 12. This is my value of about 12.2. That's my A value. So if I'm here at 56, so I'm going to go 56 minus 12.2. So I'm going to be here then at 40. That should be 12.2. So it's going to be 43.7 or 8 instead of 2. I didn't type it in right, but you guys can hopefully figure that out. So 56 plus my 12.2. So you can see where I'm going. So I'm going to have, again, my 12.2 in this direction. So this value is going to be here at 68.2. So you can see these are my vertices. I'm going to go up my B value. So in this case, B is, oh, these are going to be my co-vertices. Remember when we talk about these, they have them as your A squared is always the larger value for ellipsis. Different than the hyperbolas. To be honest, it doesn't matter really which one you do, A squared and B squared, except for when you subtract them, you can't have that negative value for your C value. So this should have actually been labeled as my B squared. This should be as my A squared because this is the bigger one. Hyperbolas, your A squared is always whatever's first. Always whatever's first. So I'm just going to switch these here. The values are still the same. When I say the values are the same, this was underneath my X, so that's why I went along my X axis way. So I kind of probably threw you guys off there. So remember, we talked about ellipse, they always do our A squared as the larger one. So this would be my A value is going to be 16. So if I'm going to go up 16, that's going to be my vertice. Because it's further away, you'll see that it's going to be a bigger difference. So my A value, again, is 16. So if I'm here at 28 and I want to go up 16, then I'm going to be up here at 28 plus my 16. I'm going to be up here at 42. So this point's going to be here at 56, 42. My other vertice, then I'm going to go down 16. Obviously, this isn't going to be to scale. So I'm going to have my other vertice right here. So I'm going to go down 16. So it's 28 minus my 16 is going to be here at 12. So this other vertice here is going to be at 56, 12. And you could kind of, well, just kind of, obviously this is not to scale. Looks more like a circle, but you guys get the idea. So easy to find the values. All I'm doing is focusing here at my center and I'm adding or subtracting those A or B values. Okay, so why do I care about this? Well, it says the major axis is what? Well, my major axis goes from vertice to vertice. So if I look here from vertice to vertice, this is what we call our major axis. And that major axis is going up and down, so we call that vertical, not horizontal. It says that my center is at negative 56, negative 20. That is not correct. It should have been positive 56, positive 28. So that is also not correct. It says the length of the major axis is 32. Well, we said that this is going to be 16 and this is 16. So 16 plus 16 is going to give you 32. That is correct. That is correct. My minor axis is 150. So my minor axis 150. My minor axis is going to be my about 12.2 plus a 12.2. That is not going to give me 150. That's going to give me 24.4 approximately, because this is a rounded value. So that's not correct. Then the last one says one of the foci is approximately at this value. So I need to figure that out. If I put this in calculator form, so if you're using the calculator for this value, then you can also do 28 minus the square root of 106. And I get 17.7. So I can also use this value as 17.7. So however you want to look at it, you can have it in radical form, or you can look at this as 56 and 17.7. They're the same. They're going to be, it's going to be one of those two values, just depending on how you look at it. So you can always change an answer to be in the format that you're using. So here's what I need to figure out then is, if I'm talking about my foci, I need to know what C is. So I know, because I have an ellipse, C squared is equal to A squared minus B squared. This is where I know which one, the bigger one, has to be first. So it's going to be C squared is going to equal my A squared is 256 minus my B squared is 150. So my C squared is going to 56 minus 150. 256 minus 150 is going to be 106. 106. So C then is the square root of 106. Okay, so I need to figure out where is that C value going to be. So I know then that I'm going to go up a value of C from my center. I'm going to go up a value of C. So this is going to be my value of C, which is the square root of 106. Or if you wanted to, you can use your 10.3. 10.3. So I could use 10.3, whatever is easier for you guys. Honestly, whatever you feel like is easier for you guys. So it's up a value of 10.3, and it's also going to be down a value of 10.3. Now remember, my X value here is still the same. My X value is still going to be that 56. So that is definitely true. Here I'm at 28, and I'm going to go up 10.3. So if I'm up here, so it's going to be 56. Oops, and I'm going to go up 10.3. So if I'm at 28, it's going to be 38.3, or I'm going to go down 10.3. So if I was at 28 there and I go down 10.3, then this foci is going to be at 56,17.7. So here's where my two foci are. 56 and 38.3 and 56, 17.7. And look, that one matched up. Or you could have used 28 and you added the square root of 106 and 28 minus the square root of 106. So just depending on which one you want to do. This looks like a chaotic mess. Hopefully you're able to follow it as I was writing it on instead of trying to look at it now. So again, always starting from the center and adding or subtracting depending on which direction you're going. So in this case, since I'm changing things going up and down, it's affecting your Y value, but your X value is staying the same. Alrighty. I think these ones are the hardest. So I'll try to do a visual with you guys. Hopefully you guys can understand it enough to see what's going on. Okay, so we have a clap of thunder. I do want you guys to look that all these equations are going to be hyperbolas, so you know you're working with a hyperbola. And it says that a clap of thunder is recorded at two weather stations that are 2 miles apart. So I have two weather stations. Station A, station B. So X comes first, so I'm going to do it horizontally because it's along the x-axis. All right, so I know that these are 2 miles apart. If that's the case, then directly in between them would be my center, and each one of these centers is 1 mile, right? There's a different distance to each one of those is 1 mile. You guys following me so far, hopefully. Station A recorded the sound 3 seconds before station B. Since 1 mile is 5,280 feet and assuming sound travels at 1,100 feet per second, which equation can be used to determine the location of the thunder? Okay, so here's what's happening. We have some thunder outside here. We have our thunder. There's my lightning to show my thunder, and it's making some sound. And at station A hears it 3 seconds before station B does. I know, so notice that this is in feet. They gave me that 1 mile is in feet. So instead of using this as 1 mile, I'm actually going to change this to 5,280 feet so that my units are going to be the same throughout because this is in feet per second. So I'm just going to mark it here then that this is going to be 5,280 feet. So here's the trick. What are these representing in my hyperbolas? These are actually representing my foci. They're representing my foci because remember when we add the sum of the foci that it has to equal, it's going to have a constant sum. So when I have my A squared and I add it to my B squared, it equals that C squared, which is that distance here. So when I do some my distance, well, from my center. So when I do my C squared and I add my a squared and my b squared, it's going to be a squared and my b squared. It's always going to be that same constant. So wherever this thunder is, this is always going to be the case. A squared plus b squared is always going to equal c squared. So as this moves around, it's always going to have that same value when I add the sums to get to my foci values. I'm always going to have that constant difference wherever that might be. So this will never change. And so that's that difference from the foci. So the lightning is going to be closer to A because they kind of hear it first than it is to B. But if it's switched to B, there's still going to be that same constant difference of that C values. So these aren't going to represent vertexes because that wouldn't be something that can change as the thunder moves. So the foci, think about it as those are the ones that are connected to something that can shift around. Vertexes are just going to be stuck where they are and doesn't have any effect on it. So if that's the case, then I know that this is going to represent my C value from my center to station A, my center to station B. Those are my C values to get to my foci. Okay, well, if those are my foci, and I know I'm working with some hyperbolas, we're talking about it then having something that looks like this. So we need to figure out, well, what is this V value? What is that V value going to be? That V value is going to come from the idea of how fast the sound is going to travel and where that's going to happen. So we know sound travels at 1,100 feet. When it says per second, that's usually we write it as feet per second, like miles per hour. So it's saying it's divided by the second. So I'm going to write it like this, just as a visual. So normally we write it like that. That's the same thing as writing it like this, right? Well, we're not looking, when we talk about our graph here, we're in feet. We're not in feet per second. We're looking at just a single linear value here. We're not putting it as the graph with a slope. We're not graphing on the coordinate plane where we'd have feet as our x-axis and seconds as our y-axis. We're looking at this here as a linear value, basically. So we're not having these two pieces. So if I'm only focusing on my units of feet, I want to get rid of the second, and that's where the idea of this 3 seconds comes in. So for every 1,100 feet per second, and I'm looking at a 3 seconds, how far away is that value going to be? Well, that's going to give me a value, then these seconds cancel out. So that's why I want you to see that idea. The second is going to cancel out with the second you're dividing by, and it's going to be 1,100 times my 3 seconds. So that's going to leave me with 3,300 feet. Okay, so that's going to be the entire length from vertex to vertex. This is going to give me my length from vertex to vertex. So if that's going to be vertex to vertex, then 3,300 divided by 2 is going to get me to the center, and that's 1650. So what do I mean? What exactly is going on? Okay, so from here to here is going to be 1,650. From here to here is going to be 1,650, because this entire length in between is this 3,300 feet. So 1650, 1650. If these are my vertex, then these would have to represent my A values. Okay, so how do I know that that's going to be the case? So what this is figuring out is that there's a 3 seconds difference before it's going to get over here. So it's, if I hear it here, I have a delay of 3 seconds. So I have a delay from here until I get to here, which is that 3 second delay. That's that 3 second delay that we hear. So how far is that delay apart? And that's what you're calculating here. So this is a 3 second delay from when you hear it at this vertex creates that sound till this vertex, there's that 3 second delay. So we had to figure out, well, how far away then is that distance? And that's what you're calculating here. Okay, so that still doesn't give me any answers. What I know now is that this A value is 1650. So if A is 1650, then A squared is going to equal 2722500. So I could look here and I can see, well, this isn't squared, so it can't be this one. This doesn't even match. And this number is too big. So I can see right away it's going to be this one, but I want to double check my math. So this would be my A squared. This would be my B squared. How do I know that my B squared matches? Well, if we have in a hyperbola, then C squared is equal to A squared plus B squared. And I know my C is 5,280 squared is equal to 1,650 squared plus my B squared. I'm going to subtract 1,650 squared from both sides. I could write those out and solve them there, but I'm just going to plug into my calculator. So I'm going to leave that all together. So 5,280 squared minus 1,650 squared is going to equal B squared 251,559, which is exactly what we got right there. So I want you guys to see how it actually works. So just from finding A, that was the only one that matched. That's not always the case. You need to know how to work it all the way through. So if I find my B squared, there it is right there. So I think this one right here is the toughest out of them all. Alrighty. Gonna flip. I have two more examples. This one I think is pretty easy for you guys. So I have the outer edge of a circular saw whose dimensions measured in inches can be defined by the equation. I do not like how it continues like that, but it's x squared plus y squared is equal to 33.0625. A hole needs to be cut in the center that can be defined by the equation x squared plus y squared is equal to 3.0625. The centers of the two curves are blank. The differences in diameters of the circles is blank. Okay, so there's a couple of things going on there. So here's my first equation. And this is my r squared value, right? So then r is going to be, if I put it in my calculator and do 33.0625, and I'm gonna, you could take the square root. I didn't hit the square root button first. I'm gonna just raise it to the 0.5 power. So r is 0.75. In this case, my r is, so again, I could do the square root first if I wanted to, 3.0625. And here my r is, so this is r squared, then r is 1.75. So here's what's going on. We have, again, a circular saw. And it has a radius of 5.75. And then it says a hole needs to be cut in the center so that it fits this equation. So I'm going to cut a hole here. And if I cut a hole, this hole, that radius of that hole is going to be 1.75. It's asking for the difference in diameter. So it says the center of the two curves are what? Well, when I look at the center here, the center of my circle for the little one is here and the center for my big one is here. So it's a drop down, so you'll be able to see the correct wording. It's going to be at the same place. They're at the same center because I'm cutting out the center of my big one, right? We're trying to cut out the center of the big one, so I need to line up the centers to match. So this right here all the way across, I want the diameter of this. The diameter, or 2 times the radius, is going to be 11.5. Here, the diameter of my little one is going to be 2 times 1.75, which is 3.5. If I want to know the differences in them, subtract them, and it's going to be a value of 8. So the difference in the diameters of the circle is 8 inches. If they want the difference in the radius, it would be 4 inches. So if the difference is 4 inches, remember I times 2 to get to the diameter, it's 8 inches. So you can see the correlation depending on what they're asking. So make sure you read it carefully, because in this case, they're talking about the difference in the diameters, not the radius. And you're done with that problem. So this one I think was an easy visual for you guys. Remember that this is your R squared always. Use a calculator. And my last one, I don't think this one's too bad either. And so it says, there's a park in Washington, D.C. called the Ellipse. What kind of shape do you think it's going to be? An event planner plots the park on a coordinate plane. The table contains the points along the perimeter of the park. All right, so let's plot these. I'm at 0, 445. I'm at 530, 0. I'm at 0, negative 445. And I'm at negative 530, 0. Obviously, it's not perfect, but you guys get the idea. So here's my park, the perimeter of the park. Okay, so then it says, the event planner wants to put a podium at one of the foci, which describes where the podium could be located relative to the center. So the center here is going to be at our origin, right? Because everything is equal distance. So what do I know from looking at this? Well, my center here is at the origin. I know that from here to here, for an ellipse, the longest value is going to be my A. So in this case, A, the distance from my center to my vertex is going to be 530. This is going to represent my B value. These would be my co-vertices. B is equal to 445. Now, it's saying that the podium is going to be at my foci, And remember, it's always going to be on that major axis. So it's going to be somewhere on this green line. So I need to figure out, well, what is that C value? We need C because we want to figure out what our foci is. So this C is not the C labeled for center. It's the C for my foci. So remember, if it's an ellipse, C squared is equal to A squared minus B squared. So C squared is equal to 530 squared minus 445 squared. C squared is equal to, I go to my wonderful calculator and I just type in 530 squared minus 445 squared is equal to 82,875. And I'm going to go ahead and take the square root of that answer. And I can see that C, notice these are all whole numbers. So I'm going to round it to my whole number. So C is approximately 288. All right, well, 288 is my C value. So I can see I'm on the right track. It's not going to be either one of those. So what is this telling me? That's telling me then if my C is 288, I'm going to go 288 to the right, and I'm going to go 288 to the left. So my podium's at one of these two spots. So what does this tell me here then? I have 288 feet south, 288 feet west, and it's saying from the center. So if I'm here, am I going to go 288 feet south or west to find where the podium is? Well, remember, north, east, south, west. So when I look here, if I'm going to go 288 feet south, 288 feet south would be up here. Oh, sorry, would be down here. South is going down, so this would be south. So it's not south. And if I look here, if I go west, west is this direction, and I would get to my podium, my foci there. So this is correct. So I needed to look at the direction here. So I could have gone west or I could have gone east, depending on what my options were to get to one of my foci. So again, that's because this was my major axis was horizontal. So I'm going left and right. So in this case, it was west. South would have been down here, and that's not correct. So using the directions. If you guys come across any problems working these out, let me know. Try your best. I know that these are difficult figuring out what exactly am I looking for. Do your best, see what you could come up with, look at your answer choices. You have a wonderful day, you guys. And if you need anything, feel free to reach out to me. Take care. Bye.